math people. Today I would like to revisit the debate of the sum of all natural numbers. So previously we investigated the claim that the sum of all natural numbers was -1/12. Believe we successfully dispelled that myth based principally on something called the nth term test for divergence to show that the different series used in that claim were not even convergent series. There's another one I saw, however. So there's another theory about the sum of all natural numbers. And again, those are numbers 1 plus 2 plus 3. So we're talking about adding all those numbers up from 1 all the way to infinity. And the new claim is that the sum is yet again a fraction and yet again a negative fraction, in this case -1/8. So I now want to investigate that claim. And actually, in my opinion, this claim is a little more convincing than the claim of -1/12. So I'm going to present the claim to you. I first saw this with Black Pen, Red Pen, another great math channel that I enjoy their content. I believe he said one of his students came up with it. I'm actually going to take it a little bit farther than he did, and then at the end we'll see if this is a justified way of doing this. So let me show you how it works. So the method is all about breaking up these numbers into partitions of equal length. So what I mean is I'm going to partition these numbers into groups of 3. So I'm going to take these 3 guys, these 3 guys, those 3 guys, and I will continue partitioning off in groups of 3 all the way to infinity. And I'm going to get the sum of each partition. You may notice that I didn't use this number 1, the first number, in my first partition. There's a reasoning behind that we'll get into a little bit later. But for now, just recognize I didn't include 1 in the first partition. And these partitions are of equal length, so each partition consists of 3 consecutive numbers. So what I would like to do is just sum these numbers up of these partitions. We should notice some pattern. Okay, so I'm adding 2 plus 3 plus 4, that's 9. 5 and 6 is 11, plus 7 is 18. 8 and 9 is 17, plus 10 is 27. And then after that you would have 11 plus 12 plus 13, which is 36. And after 36 you would get 45, and then 54, and then 63, etc. So you can see the sum of the partitions are increasing by 9, 18, 27, etc. So, and again, this is the sum we call S. And again, I didn't use this 1. So what you can see is S is 1 plus 9 plus 18 plus 27 and so on. So what you should notice about the numbers following 1 is they're all divisible by 9. So why not factor out a 9? So therefore S would be 1 plus 9. So if I factor out 9 from 9, I get 1. Factor out 9 from 18, I get 2. 9 from 27, I get 3. And so on. So what you should see is S is 1 plus 9 times the sum of 1 plus 2 plus 3, etc. on to infinity. What is 1 plus 2 plus 3, etc. on to infinity? That's S. So what you have in parentheses here is S. So we can say S is 1 plus 9S. And from there we can do the algebra. You can subtract 9S from both sides and you'll get -8S equals 1. You can divide both sides by -8 and you'll get S is -1/8. So that's one way of getting -1/8 with a 3-number partition. I claim I can get it with multiple partitions. In Black Pen, Red Pen's video, he did it with 3 and he did it with 5. I'm going to do it with 3 and 5 and another number, another finite number, and then I'm going to show you how this works for an infinite number of partitions. Okay, so we did it with 3. We got -1/8. Quite interesting. I'm now going to do it for 5 and see what happens. So I'm going to put my numbers, extend my number line down here so I can fit all this stuff in. Okay, so I'm doing a similar method. Instead of a partition of 3 numbers, I'm now going to use a partition of 5 numbers. Now, recall when I used 3 numbers, I didn't use the first number in my first partition. Now, for reasons you'll understand later, when I do this partition of 5, I'm not going to use the first 2 numbers in my first partition. So I'm not going to use 1 or 2, 1 and 2 in my first partition. So my first partition is going to go from 3 to 7, those 5 numbers, and then from 8 to 12, those 5 numbers. The next 5 will be from 13 to 17, but I'm not going to do that one. You can easily see from here, follow the pattern of what's going to happen. Okay, so let me sum up these partitions. So these are nice partitions where you can use the summing technique of outside going in. What I mean is you have 3 and 7, which is 10, 6 and 4, which is 10, that's 20, plus 5, 25. Here you have 8 and 12, which is 20, 9 and 11, which is 20, so that's 40, plus 10, 50. And the sum of the next group would have been 75. If you don't believe me, you can go and add up the numbers from 13 to 17, and you're going to get 75. Following 75, the next partition would have been 100, and then 125, and then 150, etc. So each partition's sum is increasing by 25. So what we have, and again, I didn't use these first 2 numbers, is we have that S is 1 plus 2 plus 25 plus 50 plus 75, etc. Now again, you should notice the numbers after 2 are all divisible by 25. So we can factor out 25. So S is 1 plus 2 plus 25. So I'm factoring out 25. 25 from 25 is 1. 25 from 50 is 2. From 75 is 3. From 100 is 4. So once again, what we have in parentheses is S. So S, again, we didn't use the first 2 numbers in the sequence. So we have this 1 plus 2 here, which equals 3. So S is 3 plus 25S. So again, simple algebra will subtract 25S from both sides. That'll give us negative 24S equals 3. Divide both sides by negative 24. S is negative 3 over 24, which reduces to negative 1 over 8. So again, we get negative 1 over 8. Like I said, this particular method is more convincing to me than negative 1 over 12. Now, these are the 2 ones black pen, red pen did in this video. I'm going to go a step further. I'm now going to do another partition. But before I do it, I'm going to point out a couple things that you should be able to anticipate if you understand the patterns that have occurred thus far. Now notice the first partition, we use 3 numbers in each partition. The sum of the first partition was 9, and then the next one was 18, and then 27. You may notice that 9 is 3 squared. So the sum of the first partition was equal to the number of numbers in the partition squared. A similar case happened when we used 5 numbers. So when our partition consisted of 5 numbers, the sum of the first partition was 25, which was 5 squared. You may have also noticed in the first partition when we used the 3 numbers, we didn't include the first number in the first partition. In the second partition when we used 5 numbers, we didn't include the first 2 numbers in the first partition. So we did 3 and then 5. So guess what number I'm about to do? Of course, 7. So there's a reason we are only using odd numbers for these partitions. And now I'll get to that following this example. So I'm going to use a partition of 7 numbers. And guess how many numbers are not going to be included in the first partition? The first 3. Alright, so let's look at it. Okay, so this is going to be a partition of 7 numbers. And I'll continue the line down here. And I'll stop at 17. So stopping at 17 will allow me to do 2 partitions of size 7. And again, we can easily tell what else is going to happen because of the patterns we have observed thus far. So my first partition, again, I'm not going to include the first 3 numbers. So the first partition is going to go from 4 to 10. There's 7 numbers there. The next one is going to go from 11 to 17. There are 7 numbers there. So based on what we saw thus far, we should expect this first sum to be 49. And we should expect the second sum to be 98, 49 times 2. And the next sum to be 147, 49 times 3, based on what we've seen thus far. So let's see if it holds. Okay, so let's sum this stuff up. Let's see. Well, this is 10 here, and 4 and 6 is also 10. That's 20. 8 and 7 is 15, plus 5 is another 20, that's 40, and then 9. So yes, indeed, we got 49. So let's see if we get 98 here. So let's see what we can do. Well, we can add 13 and 17, that's 30. 14 and 16, that's 30, so that's 60. Add 15 to that, that's 75. 75 and 11 is 86, and 86 and 12 is, 98. So we did get 98. The next 7 numbers would have been 18 through 24. Those should sum up to 147. If you don't believe me, go ahead and add those numbers up. You're going to get 147. When you finish, come back and join us. So what we have is S equals 1 plus 2 plus 3 plus 49 plus 98 plus 147, and so on. So let's say I add these numbers, 1 plus 2 plus 3, that's 6, I believe. So S is 6 plus, again, the numbers after 3 are all divisible by 49, so I'm going to factor out 49. So plus 49 times 1 plus 2 plus 3, etc. And of course, this is S, as you know. Hence, S is 6 plus 49S. Now we're back to basic algebra. We'll subtract 49S from both sides, and we'll get negative 48S equals 6. Negative 48S equals 6. And we'll divide both sides by negative 48, and we'll get S is negative 6 over 48, which once again, negative 1 over 8. Alright, so we showed for 3 different partitions that we got negative 1 over 8. But showing 3 is not sufficient to prove something works. You have to show it works for any particular number. In this case, any particular odd partition. So let me demonstrate that this will work for any odd partition, no matter what it is. So I'm going to assign some variables. So I'm going to assign a variable P. And P will represent the number of numbers in the partition. So, for example, the first one we did, that was when P was 3. There were 3 numbers in a partition. The second one we did was when P was 5. The one we just finished when P was 7. I'm also going to use a variable for C. And C is going to represent the number of numbers that are cut off from the first partition. So C is the cutoff number. So C represents the number of numbers that are cut off from the first partition. If you notice, when we did the first one with 3, we didn't use the first number in the first partition. So for that case, C was 1. When we did 5, we didn't use the first 2 numbers in the first partition. So in that case, C was 2. And then the one we just finished, when we did 7, we didn't use the first 3 numbers in the first partition. So in that case, C was 3. So there's an interesting relationship between P and C. Let's look at it. So based off the partitions we just did, for instance, when P was 3, when there were 3 numbers in the partition, the number of numbers we cut off was 1. When P was 5, the number of numbers we cut off from the first partition was 2. And when P was 7, the number of numbers we cut off from the first partition was 3. So there's a linear connection between P and C, which I hope you can see. So I would like to write a formula to represent that. And so if you look very closely, P is 2C plus 1. So if you can look, it should make sense. So for instance, when C is 1, this is 2 times 1, which is 1. I mean 2 times 1, which is 2, plus 1, you get 3. When C is 2, this is 2 times 2, which is 4, plus 1, you get 5. And when C is 3, this is 2 times 3, which is 6, plus 1, you get 7. So it's obvious this relationship holds for this particular case. And I think it's understood, but I want to state it explicitly here, that P and C are natural numbers. So P and C are natural numbers, meaning the numbers, they are positive whole numbers, positive integers. So 1, 2, 3, and 4, like that. So if this is my relationship with P and C C are natural numbers, the fact that P is 2 times a natural number plus 1 implies P is odd. So in fact, one of the very definitions of an odd number is 2 times a natural number plus 1. So 2 times any natural number is an even number. Any even number plus 1 is an odd number. So this implies that P is odd. Hence, we've been using only odd partitions. I would also like to write an equation of C with respect to P. So I want to take the same equation and solve it for C. If I solve it for C, I'll get C is P minus 1 over 2. So C is P minus 1 over 2. I'm going to use this relationship in a second, so it's fairly important to me. Okay. So let's try to devise a formula where we can solve it for any value of P, any particular value of P, and we get our answer. So before I do that, however, I want to point out something with concrete numbers, and then I'll make the formula. So, and I'll use the easiest example we use with concrete numbers. And let me stop there. So let me include the 5 and the 6 and the 7. So this is the first partition we did, if you recall. And in this particular partition, the value of P was 3, obviously, and C was 1. Now when I was summing these partitions, this is an arithmetic sequence, arithmetic series, excuse me. And when I was summing this, these sums are called a partial sum. So there's actually a formula to find partial sum of an arithmetic series. And that formula is S sub n is n over 2 times a1 plus an. N is the number of numbers in the sum. So for everything we do, n is going to be p, because it's going to be p numbers in every sum. A1 is the first number in that particular series, and an is the last number in that particular series. So, like for instance, for this sum, and we already know that this partial sum is 9. I mean, it's very easy to do. We can just add these three numbers. But let's say, for instance, p was 1,000,007. So if p was 1,000,007, then we don't have time to sit there and add all those numbers up. This formula works a little bit better. But just to show the use of this formula on these three numbers, so there's three numbers here. So if I was doing a formula, I would have 3 over 2 times my a1 is 2, my an is 4. So that's 6. So that's 6 times 3, which is 18, divided by 2, which is 9. So that's just showing that the formula works on this little small finite partial sum here, but it works in general. So for every sum we do, again, our n is going to be p. Now for our first partial sum, our first partition, a1 is going to be the number after c. So a1 is going to be the number after c. Again, c is the number that's being cut off from the first partition. So a1 for the first partition is going to be the number after c. So we're going to do the sum for the first partition. We know n is going to be p. a1 is going to be c plus 1. a1 is c plus 1. Well, what's c? c is p minus 1 over 2. So a1 will be p minus 1 over 2 plus 1. So that's the a1 we're going to use for this particular formula. Now, an is the last number in the series, and an easy way to think of an, I erase the numbers, I'll bring them back. So we're looking at this first partition, and the easiest way to think of an, which in this case is 4, is c plus p. 1 plus 3 is 4. That's the easiest way to think of an for the first partition. So our an for the first partition an is c plus p. Again, c is p minus 1 over 2, so an is p minus 1 over 2 plus p. Okay, so I have my an, I have my a1, I know n is p, so I can use the formula that was shown before, and this should give me the sum of the first partition. Now remember, the sum of the first partition, when the partition consisted of 3 numbers, we got 9. When it was 5 numbers, we got 25. When it was 7 numbers, we got 49. So the sum of the first partition should be p squared. P is the number of numbers in the partition, and so the sum of that first partition should equal p squared. Let's see if that happens. Okay, so let's plug this stuff into the formula. So we'll call this partial sum SP, and it will be P over 2, and my A1 is P minus 1 over 2 plus 1, and my AN is p minus 1 over 2 plus p. So now we just do our little algebra and see what happens. So let's see, p over 2. Okay, let's add this junk up. So p minus 1 over 2 plus p minus 1 over 2 is just p minus 1. Here you have a half of p minus 1, another half of p minus 1. Add them together, you just get p minus 1. So this is p minus 1. And you have the plus 1 here, and you have the p here. So hopefully you can see the minus 1 to plus 1 cancels, and p plus p is 2p. So we have p over 2 times 2p. So the 2's will cancel. P times p, p squared. It works. So we get p squared. So the first part proves to be correct. Now you remember the sum of the first partition was p squared. The sum of the second partition was 2 times p squared. Like it went from 9 to 18, or from 25 to 50, or from 49 to 98. So that's going from p squared to 2p squared, then to 3p squared, and off into infinity. So I'm going to do two things. I'm going to show that the sum of the second partition is going to be 2p squared, and then I'm just going to show in general, inductively, that the sum of any the difference between the sum of any two consecutive partitions is going to be a sum of p squared, meaning we're adding p squared to each partition to get the sum of the next partition. But first I'll just show that the sum of the second partition is going to be 2p squared. So let's take a look at that. And before I write it, so you can fully understand it, let me again bring in the regular numbers. Okay, so we already devised a formula for sum of the first partition. We got p squared. We're now going to devise a formula for finding the sum of the second partition, and we're going to see if we get 2p squared, which we're expecting to get. So I want to draw some parallels here. So for this case, this guy 2 was considered a1, and this guy 4 was considered an. So let's concentrate on an. That's going to be the important number for these numbers. So this is an, correct? So for us, this was an. All right, this is an, the last number of the first partition. So this is my an, correct? So what's the relationship between an and the a1 of the second partition? It's just plus 1, right? So to go from the last number of the first partition to the first number of the second partition, you simply add 1. So for the second partition, a1 is going to be this plus 1. So I'm claiming that a1 is p minus 1 over 2 plus p plus 1. It's just one more than the an of the previous partition. Now let's look at an of the second partition. Here's an of the second partition. Well, let's look at an of the first partition, and it's simply 3 more. An of the first partition plus 3, or plus p, gives you an of the second partition. So to get the an of the second partition, you take an of the first partition and simply add p to it. So again, this is my an of the first partition. To make it an of the second partition, I'm simply going to add p to it, and which is just going to turn that to a 2p at the end. So my an of the second partition is p minus 1 over 2 plus 2p. So there it is there. And so now we're going to throw it all into the formula and see if we get 2p squared. All right, so this was the sum of the second partition. So I'll call it S sub 2p. And again, the length of every partition is p. So the first part is always going to be p over 2. So p over 2 plus a1. My a1 is p minus 1 over 2 plus p plus 1. My an is p minus 1 over 2 plus 2p. Okay, so let's do a little bit of algebra, see what happens. So the sum of the second partition, and I'm calling that 2p, not sp. So it's p over 2. Okay. So once again, p minus 1 over 2 plus p minus 1 over 2 is p minus 1. P minus 1. And see, what else do we have? We have a p and 2p, so we have 3p there, and then a plus 1. So I'll put the plus 1 and then 3p. Okay, so you can clearly see that the minus 1 plus 1 is going to cancel. And so we're going to have p plus 3p, that's 4p. So the sum of this second partition is going to be p over 2 times 4p. 2 will go into 4, call that 2p times 2p is 2p squared. So as we expected. Just like we went from 9 to 18, 25 to 50, 49 to 98, we went from p squared to 2p squared. Again, we've demonstrated that works. But again, we've just proved that the sum of the second partition is going to be 2p squared. And so we have to prove that the sum of the third is 3p squared, etc. The easiest way to do that is just to prove that the sum of each partition to the next is a difference of p squared. So now we're going to prove, which will give us the difference of every partition is a difference of p squared. So if we know the sum of the first partition is p squared and every subsequent partition is p squared higher, then we'll prove for an infinite number of partitions it's just going p squared higher. Alright, so let's see if we can do that. So now we have to be a little bit more generic in our approach. So this is not the first partition in particular or the second. I'm going to show two different partitions. They could be anywhere. It could be the 99th and the 100th, the 50th and the 51st, whatever. These are any two partitions. So I'm going to take one partition. So I'm going to call this sum A. And again, it'll always be p over 2, so the size of each partial sum is going to be p, obviously. And now I'm going to take any generic A1. So I'm just going to say A1, because it could be different things. So any generic A1, so this is the first number of this particular partial sum. And I'm going to put any particular AN. So for any partial sum of size p, if the first term is A1, the last term will be A1 plus p minus 1. So the last term will be A1 plus p minus 1. Now that may not make sense, but I'll show it with concrete numbers. So again, we'll use the same guy we've been using. So look at here, again, in this particular scenario, p was 3. Okay, this is my A1, correct? And my AN is 4. That's my A1 plus p minus 1. P is 3. 2 plus 3 is 5. But AN is 4. So it's times p minus 1, which is 2. 2 plus 2 is 4. So when you have three numbers like this, the difference of the last two numbers of the first and last number isn't 3, it's 3 minus 1. So that goes for any list of numbers. If I have a list of 10 different numbers, for instance, 1 to 10 is 10 different numbers, but the difference of 10 and 1 is 9, so it's the number of numbers minus 1. So the last number is A1 plus P minus 1. Okay, so that's the sum, that's the partial sum A. And now I take a partial sum B, and this is just the sequence, the partition that follows this particular partition. Again, it's not necessarily first and second, they're anywhere. These are just two consecutive partitions. So partition B, so again, this is A1, this is AN, correct? Now, AN of the next partition, excuse me, A1 of the next partition is just one more than your AN. This is my AN. So the A1 of the next partition is simply this number plus 1. And so if you add 1 to this, it's going to knock the minus 1 off, and it's just going to be A1 plus P. So A1 plus P. That's my A1 for the next partition. And again, to get the AN, I simply take my A1. So again, my A1 is A1 plus P, and I add to it P minus 1. So plus P minus 1. So what you have here are the sum of two consecutive partitions anywhere in this series. These are two consecutive partitions. What we're trying to prove is that the difference of these two is P squared, meaning the difference of any two consecutive partitions will always be P squared. So if the first one is P squared, then the second one, the second partition sum has to be 2P squared, and then the third partition's partial sum has to be 3P squared, etc. If we can show that the difference of these two is P squared, then that means that this difference of every consecutive partition is P squared, which proves everything from the first partition to infinity. So let's see if that's what occurs. So let's simplify these expressions. So let me simplify the first sum. So this is P over 2. Let's see what we have over here. So basically I have an A1 and an A1, so I have 2A1 plus P minus 1. So if I distribute this P, that's 2A1P plus P squared minus P over 2. So that's partial sum A. Let's simplify partial sum B. So partial sum B is P over 2. So let me kind of simplify this. So again, I have 2A1, 2A1. I have 3P plus 3P and minus 1. Minus 1. And then again, if I distribute the P, I will get 2A1P plus 3P squared minus P over 2. Alright, so this is the second partial sum, this is the first one. So we're trying to see if the difference, so we're trying to see if SB minus SA is P squared. So we're doing this guy minus this guy. So let's see what happens. So we have SB minus SA. Okay, so if I'm subtracting, they have common denominators, so we can easily just subtract. So I'm subtracting the numerators, and I'll put the difference of the numerators over 2. So 2A1P minus 2A1P cancels. 3P squared minus P squared is 2P squared. So 2P squared. Negative p minus negative p is nothing. So all we're left with is 2p squared over 2. And 2p squared over 2 is indeed p squared. So that shows that the difference of every consecutive partition is p squared. We already showed that the sum of the first partition is p squared. So this is telling us that the second partition is 2p squared, and the third is 3p squared, etc., so forth and so on. So if you follow that, this is showing you that the sum of s in general, based off this, is always going to be negative 1 over 8. So a very convincing argument. So then the question is, so now is the sum really negative 1 over 8? And the answer is, of course not. So once again, we're dealing with a series that diverges, that doesn't converge. We can easily tell by the nth term test for divergence, which means the infinite term should converge to a number, should become 0. It never will in any of these series. So the series diverges, the sum is infinite, it's not a finite number. But you may wonder, well, why did this math make so much sense? Well, it was based off a false assumption when we were doing these little basic algebra equations, like s plus 1 equals 9s. So when we're doing this algebra, the algebra works if s is a finite number. If s is infinity, if I have 9 times infinity minus infinity, I'm going to get, yeah, you guessed it, infinity. So this is infinity plus 1, which is infinity, and it equals 9 times infinity, which is infinity. So the regular rules of algebra don't work here. So the series doesn't converge, as we stated previously. And so though this is very nice math, in the strictest forms of mathematics, this doesn't work. Now what you can do is you can redefine what this equal sign means, and perhaps this negative 1 over 8 number could be used in a unique way in a different type of situation. Perhaps the negative 1 over 12 number can be used in a unique way in some type of physics application. But when saying that, you have to state very clearly that the sum, the actual sum, is not negative 1 over 12, but negative 1 over 8. But in a very clever way, we could get those sums of negative 1 over 12 and negative 1 over 8. But in the strictest form of mathematics, the sum of all the natural numbers will be forever and a day an infinite sum.